All right, everyone. Thank you for joining us virtually. Just as a little pitch for next week, we will have our CPC, our Clinico-Pathologic Conference next week. A 74-year-old male patient presents with loss of consciousness. That'll be presented by Dr. Songal Onder. So tune in for that next week. But this week we have Dr. Justin Brooks doing Revisiting Dualism, the Mind-Body Problem in the Era of Psychophysiologic Health. Dr. Brooks received his BS in biology at the University of Maryland, Baltimore County, and he then received his MD and PhD in neuroscience from Washington University in St. Louis, as well as completing an internship in internal medicine here at the University of Maryland, and worked as a postdoctoral fellow in the Army Research Lab, and has continued to work as a locums tenens physician in multiple locations. As a physician scientist and tenured associate professor in the School of Computer Science and Electrical Engineering at UMBC, he has a significant research program using computational methods to improve human health and studying the intricate connections between physiology, psychology, and human behavior. He's also had a number of roles in the field of health innovation. He previously served as the medical director of Vanda Pharmaceuticals, and more recently, he serves as a scientific advisor at Deep Prime, a minority-owned research and development business focused on initiatives in psychophysiology and performance. And he also acts as a scientific advisor at Tanzan Medical, focused on the development of an ankle-worn wearable to revolutionize ambulatory sleep assessments. So please join me in welcoming Dr. Brooks today.
Thank you very much. I appreciate it. That was a really kind introduction. Should I go ahead and start sharing then?
Yes, of course.
All right, ready. Let's see what we got here. Share. All right, so you see slides. If I go into presentation mode. Okay, so we got all good. Everybody see the screen and everything?
Yep, looks okay on my end.
Awesome, fantastic. Well, it's a pleasure to be here, and thank you so much for the invitation to speak at Grand Rounds. It's been a while, but it's good to be back into the swing of things. And you guys heard a lot of my background already, and so I appreciate the introduction. But my sort of enduring research fascination has been around sort of this mind-body problem and how the mind and body interact and inform performance largely. You know, as you heard in my background, I've worked a lot for the Army. Still do quite a bit of work for DoD more broadly in that regard. And in there, they're looking at these issues when they think about warfighters and how they're adapting to new technologies, how they're performing. They're also worried about sort of their burnout and their stress levels as they look at, you know, sort of the changing face of war at this point. And so a lot of my time has been spent thinking about those things, but it also is very well complemented by the idea that these issues, I think, are underappreciated, a significant sort of player in the general health of our patients. And I think that there's a lot of room for us to start standardizing and thinking about these things. And I hope to convey that throughout the presentation. So the title of the talk is based on sort of one of the more recent philosophical constructs to understand sort of the mind-body problem. We'll talk about that a little bit. But I really want to communicate how I think this is an impactful sort of notion for us as medical providers. So, you know, sort of the starting off point, if you know, sort of beginning with the end in mind here, all of us as humans, including our patients, experience the world in a subjective way that really can profoundly affect our health, right? So we all experience happiness, we experience stress, we experience fatigue, we experience exuberance. We all feel depression, anxiety, lots of sort of psychological labels for things that we subjectively experience. And we know from the literature, it's replete with a number of findings showing, you know, sleep issues, anxiety issues with depression, obesity, diabetes, these types of things, that there is a sort of connection between this ethereal, almost phenomenologic experience that we have of the world and our physical health. And to date, there hasn't been really a good way to reliably use sort of develop a biomarker that captures that mind-body interaction. You know, a lot of the techniques that we use now, that we probe in social history, past medical history, and these types of things, sort of touch on some of this. You know, we have check boxes for anxiety, depression, or sort of other conditions. We also have a number of highly valid, let me say, survey instruments that can start to pinpoint different nuances and sort of the psychological framing of our patients. But how those things translate on a patient by patient level to measurable health outcomes, I think is still lacking. And I think that there is a real deficit and real need here to develop better tools that are able to objectively and repeatedly and reliably measure that link between sort of this psychological construct that we have in our physical health. And so that's sort of the take-home message that I want to bring home to you guys today is that, thinking about this and thinking about this in the context of your patient is that sort of psychological mental tapestry on which they paint the character of their life has a profound influence on their health. And it's our part of our job here, I think, is to think about how we might measure that and improve care. So, I promised a little bit of philosophical background. Largely, it's a passion for me to think about these things. I was a philosophy minor in college, and so it's always been sort of in the back of my head as I think about things. And so I arbitrarily divided this into a very brief summary of this mind-body problem and why it is. I think this helps motivate why this problem is so difficult and why this problem is so hard, because it's been an enduring issue, almost forever. And so like I said, I arbitrarily divided this into Western and Eastern approaches. There's probably better ways to divide this, but just to give sort of a background. So the first is sort of motivated the talk, and then this reflects kind of the way that we approach the problem, at least in a lot of schools here, is this dualistic idea. And so René Descartes, pictured on the right here, French scientist, the gentleman to whom we owe the Cartesian coordinate system in math, the XY sort of plot, developed that as well, but thought about this a lot. And in his construct, the mind and thoughts were distinct from the body as two different substances. So this idea that the mind was this almost ethereal, vapor-like spiritual thing that existed that sort of touched our body from time to time, right? They were aware that thoughts would control this sort of body, but it's presented this large problem of, well, how does this sort of non-real, this intangible kind of mind, this idea of consciousness, really interact with this sort of body? And that's the biggest sort of issue that that sort of the Cartesian frame of thinking had faced, is this idea of, well, how do we know that? How can something that's of a different substance affect something that is physical and something that's observable? And to him, this was sort of the ultimate sort of goal, and his proof, his ultimate sort of thought about this was, that famous quote that we all know, "Cogito ergo sum," this "I think, therefore I am." He comes back to, well, I think that the mind is really the only thing that exists, and this physical world that we have can be, I want hallucinations of a little bit too strong of a word, but this idea that it could be manifested by this sort of mind was the sort of summary of his thinking in sort of a nutshell. But this idea, what it does set up is this sort of dualistic kind of idea that there is this subjective experience of the world that we still to date have a hard time describing, interacting with the body that we can touch and measure. Fast forward a few years, we have a number of numerous very elegant neuroscientific studies, neuroanatomical studies, a much better appreciation of the brain. We have lots more computational power. We can appreciate the number of synapses in the brain, exceeds the number of stars in the known universe, these types of things. And we come up with this idea that really, well, we'll just reduce everything down to a material idea, that the mind, the subjective experience that we all have, even though it's not standard across each person, is a manifestation of our neural substrate. And so that there's nothing behind the brain, right? And there's nothing beyond the brain. And as scientists, I think we have definitely at least a bias and not a sort of predilection to really embrace that school of thought, because that's sort of what we do. We do fMRIs, we do EEGs, we do track studies, we collect empirical evidence, and we can show that if you damage the brain, you damage personality and someone's sort of percept. And so it rejected this idea of this ethereal sort of material kind of substance that was out there in sort of the beginning. But I'll put forward that despite that, in this innovation, we still don't have a mathematical description or a way to predict a thought or a feeling, and more importantly, how that would ultimately sort of affect a person's physiologic health. And to that point, the most current thinking in this, at least in sort of the more Western approaches, has been relegated to Roger Penrose and a few other other quantum physicists and neuroscientists who are coming up with theories for quantum ideas of how consciousness might be arise. And in fact, they're looking at the microtubule as perhaps an organ that is actually related to sort of quantum entanglement and coming up with ideas of consciousness. And to me, that just sort of points to this fact that we have this unresolved issue and understanding the mind. When you switch schools of thought to think about more Eastern approaches to the mind-body problem, and again, I don't like that sort of cultural division, but it's a good way to sort of parse the world. I think about Taoism, I think about Buddhism quite a bit. That really takes sort of a different view of this entirely, and for lack of a better description, in my interpretation of this, both Taoists and Buddhists sort of think about a deterministic universe that has physical laws that I'll admit can't be described by man, but there is a sort of flow or this sort of like path of the universe that emerges, and that the mind and body sort of emerge as expressions of that universe. And this idea that we have free will and we have this idea of consciousness and these feelings that we can act upon the world does exist, but our goal is seeking sort of alignment with the sort of deterministic causal flow of the world, of the universe. And so when we find this imbalance, when we get these positive, strongly positive or strongly negative sorts of feelings, we're outside of that deterministic framework, that we're sort of trying to optimize ourselves to a cost function that's already been predetermined. The Buddhists have a very similar kind of approach. They take it in a slightly tangential direction to say that they might argue that there is no such expression of an individual person in sort of the Taoist sort of flow, but rather that they have these five skandhas that describe perception, action, sentiment, these types of things that aren't a fixed body mind type thing, but they coexist and give rise to the phenomena that we experience of mental and physical states that are causally related. And so they're not necessarily separate. They reject sort of the dualistic sort of nature of thinking about a mind and body, but sort of, again, expressions of this sort of deterministic flow. And so to summarize this, this dualistic approach, this all starts with this idea that we experience the world. It's a non-standard experience that we have from one person to the next that has physical manifestations in the world that we think that we observe. And so the dualists would say there's a ghost in the machine, right? There's this magical sort of spiritual thing. Materialism says there's no ghost in the machine. It just comes from the brain. And so the Eastern philosophy says there's no machine at all. We're just part of a greater sort of energetic path. And so I put all this to say, one, it's fascinating to think about and really fascinating to see the history of thought of how people really strive to understand ourselves and the world that we live in. But two, to really point out that this is a big and deep problem, that the experience of the world that we have, how it impacts our physical world, at least the way the world that we observe, is really an enduring and a large struggle. So to sort of switch gears here and start bringing this into more sort of back down to earth, and to start thinking about this in terms of how we can start to think about how this mind and body might interact. We start sort of the central talking point of this is really the autonomic nervous system, right? And we're going to talk about the evolution of it a little bit, and we're going to talk about how sort of it works to sort of be this glue between the two, sort of this brain thing that's generating that we think is generating our consciousness and the body. And so we looked at this. There's been a long-standing sort of theory that emotion and thoughts represent sort of a dynamical system, and dynamical systems are great because they are deterministic in one sense, that they can be mathematically represented completely. They are also chaotic, which is also a good feature to have of a mathematic system that's describing something as complicated as sort of a mind-body connection, which means that in sort of a chaotic world, in a chaotic system, a very small change in initial conditions can lead to dramatically different outcomes. So, changing a tiny little decimal point here can take you on one path versus another, which is very analogous to sort of, I might respond to a math test very differently than somebody who's, a mathematician, for example. So the same stimulus provides two dramatically sort of different outcomes. And so when we started contextualizing this, we made a theoretical model here where there's can you guys see my mouse, by the way? I forgot. Should I use the pointer? Sorry. Can someone let me know?
I can see it. Can you move on to the PowerPoint and see if we can see it?
Yeah, I can
Yeah,
see it.
I think so. I think it's fine.
Okay, cool. So we have this sort of environment, stimulus, whatever it might be, that gets perceived by the brain, and the brain sort of enacts this transfer function to say, okay, well, I'm going to have to respond this way. I need to bring such and such physiological resources to bear to make this happen. It gets passed to the brainstem. We've got sensors in our carotid arteries. We did this in the context of blood pressure here. We've got pressure sensors in our carotid artery. We can change the sensitivity of the sort of our gains to that, and then we can transmit sort of effector functions through the ANS, largely the vagus, and we'll talk about that in a bit, and change sort of how our body's responding and close the loop here. And that sets up two things for us. It sets up the forward loop, this idea that thoughts and emotions, responses that are occurring up in this part can have effects on the blood pressure, and then also that the body is feeding back into this control system, so the brain actually gets sort of a barometer of what's happening in the body. And what's important about this is that you've got both components of this loop. You've got this sort of forward and backward component. And the second thing is, the vagus nerve is hugely instrumental. It's been evolutionarily conserved for hundreds of millions of years. Interestingly, 80% of the information in the vagus is afferent information, so transmitting information from the viscera and bringing it to the CNS, and with only 20% being sort of effective sort of outflow. And this sort of setup explains why you experience this idea of anxiety, and you get some people get palpitations, some people feel the change in their breathing, some people feel a very visceral, real sense of anxiety or whatever state that might be. Excitement could be another one. And why, conversely, like when you can calm yourself with breathing, with socialization, when you can calm yourself, when you can sort of think your way, bring yourself back down, you can use that physiologic loop to do that. And breathing is actually a very special case. We don't have a whole bunch of time to talk about it today, but breathing in and of itself is a very fascinating sort of function, right? Because you've got receptors in your brainstem that can switch between conscious and unconscious control, and provides an input, a conscious input into the system to help modulate it. But also a very fascinating idea, and that we can talk about in terms of how you might actually change the gains and change what's happening in this loop. This bottom picture here is the sort of last instantiation of this theory of this dynamical system, where when we think about this, when we think about emotions, when we think about thoughts, feelings, and how they might be effective, it's very analogous to how descriptions of space-time and theories of gravity, where you've got this sort of space-time rubber sheet, if you will, and you've got this planet sitting in it that creates a well and warps space-time, creates gravity, those types of things. Well, we think about emotion, the emotional sort of mind-body state space, is that as well, where you might be able to describe that rubber sheet as some function of sort of autonomic outflow. Let's say it's a composite of blood pressure, heart rate variability, breathing, pupil size, these sorts of things, and that the states that we describe them as happy, sad, stressed, not stressed, exist as wells in this rubber sheet, right? That the planet's sort of sitting on. And then that gives you a way to then parameterize that space. And you can start to think about, well, in this bottom plot, if you've got this non-stress state and you've got this stress state, we can then start to think about, well, some people might have a very wide, shallow well for their non-stress state, so it doesn't take too much energy to roll around and stay in here, and they're more restful, right? Versus somebody that might have a stress state that's very like a very deep well with very high walls that would take a lot of kinetic energy to get above this. And so we parameterize this. This gives you then a way to parameterize this in the mechanical system in terms of spring constants, coefficient of frictions, widths of wells and heights of wells and relative numbers, to say this is a way that you can start to describe if there is such a thing as an emotion and a thought that we can define in this space, how people transition to and from them, stay in them, and map onto sort of effective functions that we see and in terms of physical health. And so all of this is to say that when we're trying to glue the mind and body together in sort of whatever conceptual framework you want to put them in, we think about the ANS and we think about it as a very dynamic, chaotic process that is measurable. And so, taking this sort of a one step further into thinking about now we're going to think about biomarkers and how we could objectively measure this or begin to organize data about patients and come up with interventions about this. I motivate this from an evolutionary perspective that I think is really analogous and lovely to think about in concert with other bodily systems. So the ANS itself developed over millions of years. It was sort of the first nervous system, if you will, that existed before brains and CNS structures did. And so the very first sort of representation of this was in the dorsal vagal complex. This started in reptiles and primitive invertebrates, so like the sea lampreys, and this was about 600 million years ago. And that dorsal vagal response is what you see sometimes in reptiles, that sort of freezing behavior, complete shutdown, metabolic conservation, where they're responding to a stimulus by kind of completely pulling within themselves. Over time, that wasn't sufficient, right? Lots of reptiles and lampreys were dying, and you need to be able to run or fight or combat the stimulus or whatever you're sort of encountering to survive. And so, just like our engineers and the way that we develop things today, we developed a nervous system that superseded what went over top that dorsal vagal response that we call the sympathetic system. Can you hold 1 second for me? Sorry. I'm sorry. Truth be told, I'm on vacation and a little issue there with housekeeping. We developed the sympathetic innervation to allow us to perform these fight or flight functions and mobilize under threat, and that emerged in the bony fish, the jawed fish, about 100 million years ago. 100 million years after the more ancient dorsal vagal system. And then lastly, this ventral vagal system developed in early mammals that now allowed social connection, calmness, like the ability to exert calmness through breathing. And I'll note that this actually also sort of coincided with the development of neocortex. This idea that there is sort of a cognitive function that can influence the viscera, that can influence the sort of motivation or the activation of these functions. And so Steve Porges put forward this polyvagal theory that arranges these systems in an evolutionary hierarchy of responses. And so when one system fails, we go to the next oldest, and they're not chosen consciously. It's not like, okay, I'm going to use this system now, or I'm going to use this system next, that type of thing. They're reflexive and biologically embedded. But the way that you would traverse that hierarchy can be an individual factor, right? It could be the case that you receive a stimulus, you receive a threat, and you are able to stay sort of in this ventral space for a while and exert control and calmness and that. Or it might be somebody else might more quickly traverse and go quickly to sympathetic, or somebody might go all the way down to sort of this dorsal response. And so, the question is, can we use this framework to identify individuals that might have constants or parameters that might describe, okay, well, this person's more of a ventral person, probably going to be healthier because they don't get into these they don't bring on these endocrine functions and all the rest of this like somebody else, and then they don't completely traverse all of this to completely shut down. And what I like about this framework, and one of the reasons it's really sort of endearing and interesting to me, is it comes back to one of the more elegant things I remember from cardiology, which was the conduction system of the heart is very similar, right? So we have this SA node that sits in the top of the right atrium. It's innervated by parasympathetic and sympathetic branches. It is the primary pacemaker of the heart, gets the atria to contract, et cetera, et cetera. But if that fails in a number of different conditions, we have this backup. We have this AV node, right? And the AV node showed up. I think it was the 3-chambered heart in the turtle that we started with the AV node, and synovial node came subsequently. And if that fails, then we do have ectopic pacemakers in the ventricles, right? That can generate sort of a fail-safe contraction of whatever's in there to try to maintain life. And so when you think about these things in parallel, I like that, at least the face validity, I'd say, about having sort of this hierarchical evolutionary sort of framework to fall back on, that's mirrored not only in the vagus system, but or the ANS, but also sort of in the heart as well. And so we're going to translate this. We're going to get this down to, I guess, minimize that. I'm sorry. We're gonna translate this to something more pragmatic and a little bit more practical, and come a little bit closer down to earth here. And so I'll spend the rest of the time talking about burnout and stress as that experience, that sort of indescribable experience that we all have, and how it translates into health outcomes. So I think most of the audience here can agree that that we as Americans, and putting aside political issues and all these types of things, we work fairly hard. Our culture is sort of work hard, play hard, and I think all of us can relate to this idea that it's this feeling that you're constantly on the clock, right? You come to work, you're getting paged, you're getting pinged by a number of different places all the time. You go home, it's very similar. If you have kids, you're just scheduling activities and trying to balance PTA meetings and all that sort of stuff. And there's this constant sort of input from all places. And when it comes to work specifically, there's objective measures of that. The GDP gap between us and Europe is almost 80%. This was an article published last year, and you can see it even when you look at the state level data. Italy is just ahead of Mississippi in terms of that country's GDP relative to Mississippi, and Mississippi is one of the poorest of the 50 states. And this, you can see it all the way through. So just an amazing productivity of our culture of this, sort of grind hard, get in there, mix it up, fully commit yourself. Definitely beneficial in terms of economic output and economic production. The flip side to that, though, is that being part of this culture means that you're going to likely be sicker and die younger than people in a lot of other countries. And, I realize that, it's a big leap to say, well, this is all coming from sort of this work culture. I realize that, violence and food industries and a number of other things play a role into this. But I think that there is at least a supporting notion here that this culture of grinding and constantly overstimulating and putting people sort of in these states, in these stressed, burned out kinds of states, it's going to have long-term effects on their health, especially if you think about, you graduate from high school, let's say, and you start really sort of imbibing that culture and moving forward. You're going to start manifesting those behaviors and the sequela of those behaviors fairly soon. And so the psychologists sort of put this in a box that they call general adaptation syndrome. It's a nice framework to think about. It's very sort of an easy way to model the system, in that it starts off with this idea of having this sort of homeostatic set point that you want to maintain, and then you encounter a stressor, whatever it might be. It could be a notification from work, getting a rapid response, whatever it is, sort of on a short time scale. Your body sort of alerts initially, and sort of like takes sort of a depression. You see this in terms of like that calming sort of early vagal response, and then over time you develop resistance to it, right? You're bringing on additional resources to withstand the stress and try to drive back to this homeostatic sort of set point. And over time, right, just like any system, if you keep maxing it out, if you keep redlining it, you will eventually sort of burn out the resources there, and this is where illness and ultimately death happens. And so the really morbid experiments that started with this were, how much can you shock a mouse until it passes and stops eating, and all those types of things. But it does capture the framework of this thought of like how these issues could actually affect physical health. And so, to put this into sort of demonstrable and sort of tangible ideas here, right? This idea that our workplaces are very full of this constant, persistent demand to attention, devices, emails, all that sort of stuff. You're constantly pinging the system that was evolutionarily designed to help you respond to threats. And the rapid decision making and frequent task switching that we all have to do adversely affect the body over time. And there's, like I said, I think we're all aware of the physical health repercussions that we see as sort of a public health challenge here with weakened immunity, hypertension, diabetes, sleep disorders is a whole different sort of can of worms here in terms of how this affects people's sleep. Mental health is almost an obvious one, and then obviously ultimately reduced economic output, especially as you get to later in life, because you are missing work and missing work for health. And so the take-home point is that this is sort of a psychological model to allow us to sort of think about this process, and put together sort of how these stimuli, how this mind might affect the body over the long term. And I want to caveat that, this framework, this general adaptation framework, is something that can stretch and contract for multiple time scales. So it's not just second by second type of things. It's minute by minute, months, years, and those sorts of things. And people cycle through in and out of where they are sort of in this state pace. But again, just sort of providing a psychological framework for this phenomenon. And so the last thing that I'll get into before we get into some empirical data is, just putting the cherry on top in terms of how we think about the causal linkage between this, between this performance, this cognitive performance that we have to maintain, that we're constantly being pinged for, and physiology. And so on the left here is just a depiction of synapses in neocortex. A lot of this is a dorsal anterior cingulate cortex, a few other places, the synapse in the hypothalamus, and then connect down to the brainstem to mediate vagal outflow to the heart. We also make synapses up and down the anterior thoracic cord, right, for sympathetic outflow here. So what we're going to talk about a lot is this loop. And on the right here are some seminal studies that were done by psychologists Yerkes and Dodson back in the early 1920s, where they were trying to understand this idea of how the body influences the mind. And so here on this x-axis, they have arousal, and on the y-axis, they have performance. And this was a study done in mice where they had sort of electric floor that they could shock at any point in time. And by shocking it, they would increase the arousal on the mice. They would increase sort of the sympathetic and activation of the mice. And they had the mice performing various two types of tasks. One simple task that might be like putting a paw just on a lever to make it stop, and a more difficult task that might have had 2 or 3 steps in it to complete. And so what they showed was that as they increase the arousal, the frequency and duration, intensity of the shock for simple tasks, so like just stepping on the pedal, let's say, the more arousal, the more stimulus that they provided, the better that they performed on the task, faster reaction time, pressing the right pedal, etc. Conversely, when you're looking at more complex behaviors, that increased arousal did not improve performance, and there was a sort of sweet spot that sort of peaked in the middle here. And this is, ties back into the work that DoD is interested in and trying to keep people kind of in this sweet spot for performance. But what's interesting about this is it's a sort of, the anecdote that we tell ourselves about this is you think about athletics, and I admit that the athletics might not be considered a simple task, but when you see a sprinter sort of getting the energy from the crowd to really hype themselves up and increase that arousal, they may be trying to operate a little bit further out on this sigmoid to increase their output and increase their performance. Conversely, if you're doing sort of a complex task that requires multi-cognitive domain integration, you're working with teams and all that sort of stuff, at some point, cranking up the energy in the system here is going to cause you to make mistakes, and it's going to cause you to do worse. So this shows you that the body's influence on the mind can be profound. And on the flip side of that, when you think about sort of the resting state of the person, or the mouse in this case, and their ability to meet the needs of the environment or the stimulus, there's also some very interesting findings there as well. So in this bottom plot on the y-axis is heart rate variability. It's something in the later literature now, but this is the variability in the intrabeat interval between R peaks. This was the time domain measure of it, the root mean squared of successive differences. So higher heart rate variability means more parasympathetic tone, which may map onto more ventral tone, right? So the higher your heart rate variability is, the more calm, more parasympathetic tone you have versus low parasympathetic activity here in mice that had low heart rate variability. And what you're showing, what we're just quickly showing here is that before encountering some stress, before encountering some test, and then these two testing sessions and after stress, those that had this high heart rate variability, so this high parasympathetic tone, are able to modulate appropriately for the testing that they did and then recover, versus mice that have a very low heart rate variability effectively stayed stressed the entire time. In fact, some of their doing a task actually didn't change their recurrent physiology quite quite so much. And so you see this other sort of side of this of sort of descending control. And so that's the last sort of slide to set up sort of the theory of this. And so we'll get into sort of empirical work here. And so the first thing that we did was, well, we can understand, like I said in the beginning, we have these ideas of mental states and survey instruments that can ask somebody if they're stressed, if they're fatigued, what they're doing, and how they're doing. But ideally, what we want is to not disrupt their ongoing task, and we ideally don't want to have to deal with interoceptive bias, where they can't faithfully report their true sentiments and get something that's more real time. And so what we did was set up a machine learning model that used a single lead, lead to modification to measure their ECG while they were doing a task. And so the participants were out navigating in an environment. They were trying to count the number of objects in the environment, and every once in a while we gave them a math task on top of that. So they had to do two things at once, and that's what's marked in this red line here. So we've got time here. We turned on the math task here and turned it off, and it was done by here. And in blue, what you see is our prediction strictly based off of ECG of what was happening and to recapitulate the task structure. So, the ideal thing would be we'd have a ramp up and ramp off sort of immediately of that mirrored sort of that box plot, but, given delays and signal transduction things, it's a little bit slower than that. But what you can see is that based solely off the ECG, we are able to understand what someone's doing cognitively. Like, we can understand that there's this dual task state, and we can measure reliably. And then we validated this model in a number of different studies and a number of different data sets. The most interesting one, I'll just quickly comment here for the sake of time, is with the NASA Task Load Index. So that is a survey instrument that NASA uses to rate the difficulties of different missions that they're planning for the astronauts. In it are scales of mental demand and temporal demand. And when we look at our model output compared to what survey responses folks gave to this NASA TLX for various missions that we had them doing, we see a very strong correlation with that NASA TLX bit. So really a nice sort of construct validity measure of showing that our physiologic model, our objective model, maps onto something that's known in the literature as well. We also validated it on some other tasks and published that a couple years ago. And so now that we've got this model, how do we get into this functional phenotyping of this mind-body connection? And so what we're going to do is we're going to have people do cognitive challenges while we measure their physiologic response and look at that reflex that they have in response to the cognitive challenges. And so we have this system that tests people on task switching. Enumeration is a way that tests perception and working and perception and attention. And then we have a special working memory test. And these tasks are chosen to probe different parts of executive function. We vary the difficulty, a number of them. And while they're doing the task, we collect the ECG and run our workload model. So we take our ECG, we pull out the features, heart rate variability is one of them, among others, and then we run our model on it. And we can put those together to see how well we can characterize and measure sort of what we call a mind-body biotype, sort of a phenotype of this person. One thing I want to point out, just in case there's interest in this at some point, is that we also look at discrepancy between people's perception of themselves and what we can objectively measure. So we ask them how well they perform relative to how well they actually perform. We ask them how stressed they get versus how stressed they actually were, at least according to our model. And the discrepancy between that is also a very fascinating signal that I think requires some additional thought but something that we're looking at very actively too, because a person's perception of their reality, I think, plays a big role in terms of how they manifest health behaviors and in their overall health. All right, and so here's the experiment we did. We took a baseline. We had them watch a baseline video. They watched a lava lamp for 5 minutes. We hooked them up to the ECG, and we collected eye tracking for some additional models that we're doing. And then we get this 5-minute baseline. And then we do this testing phase where we put people in these cognitive performance tasks. We look at their objective accuracy on the cognitive tasks themselves at the various difficulty levels. And then we measure their workload and create sort of this mind-body space where we've got cognitive task accuracy on the y-axis and physiologic workload as measured by that ECG model on the x-axis. And like I said, I won't get into it here, but it is, we also look at their discrepancy, the difference between their self-reports and objective measurements that we take and combine those ultimately. And so we did this experiment in 2 groups. So the first was an esports community at UMBC. Again, this study was motivated, again, with sort of DoD interest and trying to predict performance and trying to predict fatigue over time. But then we also did expand it to the community where we had an age range from 18 to, I think, 69. We stratified for women, male and female gender, and sort of let the chips come in, let the patients come in as they would. I will say that it wasn't a clinical sample by any stretch. It was really a test to see if there was retest reliability. If we measure somebody on the system, how stable is it over time without any intervention? And so this is what the data look like. And so when we start to map this mind-body space, as I told you, this is the cognitive performance on the y-axis, the workload, the physiologic output on the x-axis. And this is a pictorial representation of the raw data. So each dot on this data on this plot represents a single person doing a single task at a single difficulty level. And so there's a lot of dots there. There's a lot of dots there. And then when we ask an unsupervised classification algorithm to tell us how many groups of people they think there are here, how many groups of dots there are here, it tells us that there's likely to be 3. This is a silhouette plot that helps sort of constrain your clustering approach. And then when we say, okay, well, we assume that there's going to be some variability in terms of what tasks people are good at and what stresses them out versus not. We're trying to get sort of a general sense of what, where a person lives. So let's just take the mode of each person and plot that and take a look at whether, where they spend most of their time. And when we do that, we get these very tight 3 clusters that I am hoping to demonstrate over time that map onto this polyvagal theory, right? So you've got a group here that has relatively low workload, relatively low physiologic activation for relatively high cognitive performance. And so this is somebody that is calm under cognitive tasking and seems to be expressing a lot of that ventral vagal tone, that most recent evolutionary type response. You've got a group here that is seemingly more sympathetically driven, so that next oldest, where you've got a relatively high physiologic activation for a relatively similar performance and sort of cognition. I mean, there is a little bit reduced sort of cognitive performance here, but if you were to look at this distribution sort of across the y-axis, they would be largely inseparable. But it's clearly costing this group a little bit more to have that performance. And so harkens back to this sympathetic, that next oldest level. And then the last is this third cluster of people, which is a little bit interesting, still sort of collecting data on this, but it does appear that clearly they exhibit that freezing behavior, right? That they're definitely characterized by having lower cognitive performance, so they're on this axis, with a predominance of higher sort of workload activation, but there is certainly an arguable spread there. But that's, to us, as as we're trying to think our way through this, maybe more reflective of that dorsal, the most ancient sort of vagal tone. And in terms of thinking about this in terms of clinical relevance, again, we did not collect these data with a clinical study in mind. We collected a few different surveys here and there. Just to tie it together, we're, again, really largely focused on fatigue and burnout. The first thing I'll say is the retest reliability was about 80%. So if you were sort of that ventral type and time 1, 2 to 4 weeks later, without any intervention, you were likely to be type 1 again. But for the people that met, the 20% of people that did change their type over time, we found a significant relationship with self-reported sleep quality, whether good or bad. And so we're very excited about that because clearly, if they were going through some stressor that's causing them to not sleep, then that we would expect that to affect their categorization. And then we looked at burnout using a Copenhagen burnout inventory, a well-cited instrument to assess burnout, and we show that certainly that type 3, that more dorsal vagal group, is showing significantly higher burnout than the others. And looking and I think the trends here is obvious. Obviously, there's quite a bit of variability. I think we can tighten up when we start to do experiments where we stratify by cluster type. And so moving forward, what does this look like in practice? We're putting this paper together now. In fact, it's under review to really look at this reactivity biotype as a potential novel insight for clinical practice. And so, ideally, the ultimate sort of goal here would be that this is a test that you could order at a particular time that you see a patient. If you think that there might be something to this, something about sort of their mental framework that affects their physical health and over the long term, and sort of repeated over time with various interventions. And so, the whole assessment takes about 30 to 40 minutes. We're still fine tuning quite a bit of the tests that are there, how quickly we can get it done, and that sort of thing. But the idea would be that this is a test that you could use to sort of biotype your patient and start to manage them accordingly. And we can talk about interventions sort of in the Q&A if there's time. So that's how we think about it. And so I want to just end where I began to say that this subjective experience of the world that we have, this non-standard, uniquely individual way that we experience the world, can profoundly influence our health. And our team's research is really looking to develop a biomarker for this that we can then use to affect our patients and improve health outcomes more broadly. And there's a lot of work to be done here, trying to figure out what conditions might be better matched to this and really fine-tuning the biomarkers. But I think that it remains a critical link in managing and caring for our patients and taking a step back to look at sort of the whole general health picture of a patient, in addition to all the wonderful work that we do with specific conditions, specific etiologies of hypertension and diabetes and things but this could play a prominent role. And just a quick thank you. I have a small but fantastic team. This is Sarah Conklin, who was with us for a couple of years. She actually just moved to Pittsburgh to lead a large women's studies. This is Quang, my exceedingly talented graduate student, expert in machine learning. Murat works with me very closely. A senior data scientist, has a fascinating background in oceanography, and has brought a lot of that to bear on our signal processing algorithms. Really fascinating work. Gulshan, as a biostatistician and computational biologist, who works very closely with us, and Jenny, our epidemiologist, to help us start corralling the right patients together and running these studies. So went a little bit longer than I was hoping to, but that concludes the presentation. I'm happy to take questions.
Thank you very much. We have a few questions in the chat that I'll answer first, then I'll get to some of the raised hands here that we have as well. So Dr. Momeni, I think more of just commentary. I do not condone working hard to promote a materialistic lifestyle, but as a physician, I prefer to do more and heal and comfort more patients in my 82 years of being then living to age 84. Does living from 82 to 84 years of age justify cutting back on what I live for? Just a thought. And then Myth McLean Weiss, what are some small daily habits that we can do that will help our body recover from constant stress at work?
Yeah, well, first, I appreciate the comment from Dr. Momeni. I think there's a lot to unpack there, but I think it's a very, very point well taken. In terms of small daily habits, one of the things that we are looking into is breath training, and I realize that that's oversold, especially in the consumer market, for how that should be done. And Fitbit and Apple Watch all have the breath stuff that they get you to time with and practice. But I think the real issue is trying to do that sort of breath training when you're actually under load. In fact, that's what Quang's thesis is going to be about. A lot of the breath training, it's like, okay, well, I'm gonna go sit aside for 20 minutes and do this breath training and practice my box breathing and all that sort of stuff, which is great. I think there is certainly some rewiring that happens there, but what you really need to do is bring that to bear when you're experiencing the stimulus that you have. And so a lot of what our work is going to look at is trying to control the inspiratory and expiratory ratio to make that a reflexive response when you're actually under sort of a stimulus or under sort of a load. But I think as gimmicky as it might sound, I think breathing is probably the key to this because, like I said, it's one of the very few volitional visceral functions that are under our conscious control, and I think that wiring is there. To allow us to impact that system. I mean, you can when you change your breathing, you fundamentally physiologically change your heart rate variability just by the inherent linkages. So I think that's the real challenge there. And then in addition to that, diet, all the normal stuff, diet, exercise, having a good social structure, interacting with the right people, I think makes a big difference. Um, all right.
Lovely.
Um,
What is the body-mind connection in successful
I don't
biomarkers?
know. Those are some crazy. That's definitely a very interesting extreme case. I can't say that I've really thought about that a whole lot. That's definitely a lot of conscious control there, and probably a lot of very significant calluses in the feet. I
Probably so.
see. I think Dr. Davis had an answer for this too. I see Dom's chair office would like to answer this question. Department.
Okay.
I left. Okay.
Karen Chen, very fascinating talk. Can you provide some insights on the how the biotypes may evolve over time through learning and training or adjust lifestyle, such as improving sleep and using meditation?
Yeah, no, I think there's a lot to that. And, to be honest with you, and this is an open call to anybody that would like to collaborate. We're looking for collaborations now. We've just recently set up a system in a sleep clinic in Delaware and another one in a local wellness clinic, an integrative sort of medicine clinic here nearby. And we're looking to see how those interventions might affect this biotype over time. Right now we did sort of a naturalistic study and just said, okay, let's measure time one, time two, without any intervention to see how stable it is. I do think that there is a lot to be said for some of these commercially available sort of holistic type treatments, and I realize the audience I'm talking to here, there's a lot of debate around them, but there's I think it's definitely a valid question to ask with rigorous methods to see how this objective measure can be modified uh, by some of these interventions. I'll say that the one that I favor the most is probably oddly enough cold plunges that has been measured and shown to create substantial vagal drive like immediately and then over the long term with repeated sessions. Some very interesting, acute phase reactant reductions and endocrine changes. So, Karen, if please feel free to ping me if you've got ideas because we'd love. I mean, the system is relatively easy to deploy now, and we can put it almost in any setting. So we're actively looking towards that.
The impact of visual impairment on the measurements that you mentioned.
Visual impairment on the measurements. Well, I mean, I think that's certainly a limitation of the method because you do have to be able to see the task when you do it on the computer. I think it's a point I hadn't considered before. Doing this sort of in an auditory-based task would definitely be reasonable. There'd be significant challenge. There'd be some new challenges there if you do it. Well, I guess you could still do it mechanically, but verbalizing things does actually change your cardiorespiratory coupling significantly, and so that would affect the machine learning there. But if I missed something about the visual impairment, let me know.
From Ian Kleckner, kind of two questions. So how much of your observations result from people actively managing their breathing versus people merely perceiving things differently? And then a
Yeah.
follow-up question, did you ask people about their affective state during the tests?
Yeah, and this is getting right to it, man. This is a great question and something that I'm still struggling with now. So, I can certainly show you offline with part of the paper that we're writing now talks about this. Number one, like the breathing, I think probably has a lot to do with it. We did not collect breathing during these couple of studies. We are doing that in the next one. It was actually trying to find a reasonable breath sensor is oddly strange, is oddly difficult. But I think we've got one, and we're going to be looking at that. But the perception piece of it, I think, is really huge. I mean, that's a big field of neuroscience, this concept of interoception, this ability to know kind of where you are in sort of your emotional and performance state. And it is really shocking to see how miscalibrated some people are in terms of how well they perform. There's people that are on either side. People that think they did really well but did terribly. People that did terribly but thought they did really well. And the stress stuff is just all over the map. There's some people that are like say they're super stressed out, but their heart rate variability and things are very low. And I'm not going to say that, on the stress idea and these, when you get into these sort of subjective things, there's a one-to-one mapping, but there is a lot there, and it does seem to be related to that functional phenotype that we were describing. We do have a whole nother study actually, where we look at sleep, and we ask people to rate, go all to the normal sleep diary stuff. How long did it take you to fall asleep? How long did you fall asleep, et cetera, et cetera. And then we do that in a control condition, but then in a experimental condition, we give them actual Fitbit data to say, okay, well, Fitbit said you slept for 8 hours. How long did you think you slept? And we get dramatic changes in those answers as well. Interestingly, we see that in people with insomnia versus not to a similar magnitude. So again, getting at this, insomnia is an interesting one because by definition, it's a subjectively defined disease. So in some sense, just providing an anchoring cue can and altering someone's perception can help potentially cure their disease, if you will. And then we did, I see Ian's got a couple. So we during the task we did, so I didn't show those data, but we didn't ask them affective state. We were asking them how fatigued and how stressed they were over time. And what you could see is that sort of dorsal group definitely depleted over time, as well as the number that sympathetic group, they're burning the gas, they're sort of redlining, and they sort of describe more fatigue and more burnout. And we had them, I'm sorry, I should have said we had them play a 40-minute video game afterwards, and we probed them every 10 minutes to see how they were feeling, and you could see them sort of steady decline based on what group they were in. That was the extent of the affective state. Again, this was like a performance type thing. How does affective state, subjective pleasantness and arousal relate to three groups? Don't have that data, but something that we would look to put into the next round. We're working on Quang's thesis data, experimental design now, so we're definitely trying to capture more health indices and definitely looking at a little bit more things to tie to psychological theory. And then Peter, I can see this. So, do you think it will be more effective? Uh, uh, do you think it will be more effective a description of your talk to say mental than mind? Yeah, I would welcome a discussion about this. The semantics around this are really complicated. Sorry.
All right, good.
Oh, yeah, the semantics around this are really, really hard. And, the precision of language, I think, is fundamentally important. I still struggle with them myself. And so, this idea of sort of mental state and mind is something that has definitely come up before. And the marriage between those two terms or where the Venn diagram of them overlaps is, I think, an open question. I think that we yeah, I think I default to mind, especially for this talk, because I try to tie it back to the philosophical construct of mind, like you said in your statement there. But that it is a mental state, especially when you start thinking about it as sort of dynamical system, I think is certainly fair game.
I think that's all the time we have. Thank you so much, Dr. Brooks. We really appreciate you coming and speaking with us today.
No problem. I hope you enjoyed it. Look forward to hearing from you. Take care.
Thank you.
So much.